did everybody have a good weekend? You're planning on an even better weekend next week, right? Far better weekend next time. All right, the only thing on the schedule for this week that's due, everybody looking at Wednesday for quiz 8. That's on the syllabus, so that'll be the next thing. Okay, to begin with today, just a very, very brief review of where we were. I won't write anything down. There were 4 options for what a potential energy diagram could look like, and there's a little bit of interpretation you put on each one. The first 2 were both for an exothermic reaction, and that means that you start one place and you end up lower. That means the reaction does want to happen all on its own. It will happen as long as you can give it enough of a kick to overcome the activation energy. Now, saying that it does want to go doesn't mean it gets there fast, right? It could take forever to get there until you give it a little boost, which is called activation energy, and that makes it go. So there's an option, and this one's exothermic. So is this one, because the only thing that you look at in deciding exothermic or not is just where you start and where you end. If you end lower than you start, that's exothermic. The words would be exothermic, spontaneous. It does want to happen. But you got a couple of humps to go over in the middle. It looks like there are 2 steps, and you got to give it a little bit of kick each time. Between the 2 humps, there's a thing called an intermediate. There's a transition state at the very top of the energy hill. We'll get some exact examples of that. And it looks like this one is, of the 2, this one's the rate limiting step. It's not always the second step. Maybe it's the first one. If you started from way down here and just had to go a little hill for the second one, okay, it's always the tallest peak from start to finish. That's your activation energy, rate limiting step. Okay, then here's one more possibility, and look at the big, big difference on this one. Where you start, and then all the stuff in the middle, compared to where you end, that's uphill. That means it's not spontaneous, it is endothermic, it takes energy to drive it. It's not impossible, just it takes that. And look at the energy of activation to begin with. That's how much you got to pay to even get it to happen. Okay, that's one step, and then 2 steps can be the same profile from beginning to end, meaning you start one place, you end a different place that's higher in energy. These are going to be less stable bonds, probably, but it can happen. And then in the middle, there would be a transition state here, intermediate here, and a transition state in both of these spots. This is, okay, I said I wasn't going to write anything. This is endothermic, and that, of course, is that term right there. It's not spontaneous. Left all to itself, it would not happen. You have to find a way to force it to happen, and that's doable. Okay, it was a lightning tour of terminology, shapes of graphs, meanings. We're about to use all of it. But are there questions on that so far? I'm curious. Does any of this look familiar from your first year course? Good. Some of you are nodding yes. Okay, so if you look at those 4 pages, you will have all the information you need for this little practice problem set. So that's a way of reviewing as well what we just touched on. So I forgot to go first draft. Pass those over. This will just be 3. Remember, you're free to look at your notes if you want to. Okay, how about another minute? Anybody think you need more than that? Okay, if you would, please pass them to your right. Is that yours too? Right here. So moving on, we'll be working on the parts that are listed in your syllabus for today. It's outlined as numbers 6.1 to 6.6. And this is a new chapter called alkyl halides. So this is a step now into new territory in the sense that every atom in the molecule isn't either carbon or hydrogen. And we had a whole chapter on alkanes. Okay, taking one step away from that, we're going to replace one, maybe two hydrogens with a halogen. So here's the story behind these things. It's compounds with this formula, Rx. Now, X is a halogen, which is going to be, well, just go down the table. Fluorine, chlorine, bromine, iodine. That's what really sets these things apart. You also got to be a little bit picky when you talk about the alkyl group, okay? Now, I'll just put the word in here. But this bond to a carbon right here has one special requirement on it. Carbon, specifically that holds halogen, that must be sp3 hybridized. Now, other than that, you can have other stuff in the rest of the molecule, and it's okay. So here's what would count. Actually, let me start out with something quicker that would not count. Okay, that's not an alkyl halide. And here's the reason. That carbon right there is sp2 instead of sp3. You want to make sure that your halogen is sitting in some spot where the carbon's got no double bonds to it. It wouldn't take much to modify this structure up here so that it would fit the definition. And all you need to do would be, I'm going to make it a little more obvious, but just one carbon would be enough. So let's really make it clear here. Okay, this one, that is something that fits the formula of Rx, and that's because that carbon right there is sp3. Now sure, there are other carbons in the molecule, like these out here, that are sp2, there are double bonds in other spots, that's okay. That one spot right there qualifies it. And why do we talk about these things so much? They are a building block for just about everything else. This is a good place to start. It will connect you to lots of other kinds of compounds. So the naming I've tried to confine to part of one page because that's about all it's worth. Now there are two different options right here. And each one of these methods is something that I give just as a little example. The first one is the so-called haloalkane, meaning you're going to name it so that it sounds like an alkane when you're all done. Okay, so that's what you can expect. And you just do this the way we would have done it in the chapter where we talked about how to name alkanes that have a little substituent or a little partner. You're going to name it for the parent alkane. And so this one's what? 2, 4, 6. Looks like this one would be number 3. So this one would be 3-iodohexane. You've done that before, and there's no stereochemistry listed there, so you skip it. And this one looks like the longest possible chain would be 3. So we'd call that 1, 2, and 3. And this would be what? 1-chloro, 2-methyl, and then name for the alkane at the end, which would be propane. Okay, that's one way to name them. Be prepared to do it that way. The bigger the alkane, the easier it is to do it by that route. But the other way to do it is to name it by an alkyl group, and your alkyl group must be one of the common ones. And so there's just a few that can be named like this. Take this one for example. Now notice, this is a little review chance. 4 carbons, not all in a row. There's one branched off the other. And your connection is not to the middle one, your connection is to one of the ones on the outside. So this is some kind of butyl group. Which one is it? It's not sec, because sec is all in a row and you connect to one of the middle ones. It's not tert because you connect there. Which one is this? This is probably the hardest to remember. Anybody know? Got to come through this several times, right? Okay, so this would be isobutyl chloride. Just for comparison, here's one sketched out to be the same carbon framework, but chlorine is here, and that one would be tert-butyl chloride. Okay, if you can do that level of examples, that's all the naming that we need to do in this class, and we will call it done with naming. So we'll start working right away on the structure and reactivity, what makes them do what they do and why they are special. So I can't overemphasize this. Maybe really exaggerate your bond here. There's the bond that makes all of these compounds the same as each other. There's one bond between a carbon, which is, okay, sp3 hybridized. And there sure is a big difference between these two ends of the bond. This one's partially positive, this one's partially negative. And maybe just to emphasize that, you can put in your lone pairs. Okay, now if you had to say one end or the other was a Lewis base, it would make sense to look at that end and say, well, it sure looks like it has electrons it can share with somebody. And that's okay. That would be the base. This one right here, the other end, the carbon, it doesn't have a full-out empty spot. But you wouldn't be far off to call this end the Lewis acid end, because even though it doesn't have a totally empty spot, it's got a partially positive spot, and that's a target for a Lewis base. So another thing other than the polarity about this is that the bond itself is worth giving some attention to. The CX bond gets weaker, and there's a trend to it. Is that on there? Yeah. Okay, think going down the periodic chart. Start with fluorine, descend to chlorine, next to bromine, and finally to iodine. Okay, up at the very top, you have a bond that's extremely strong, and down at the bottom, the carbon iodine is, to understate it, a weak bond. Iodines are famous for popping off with little to no provocation, and so in the middle, that suggests you've got some potential to tune the reactivity. If you do want your bond to be extra stable, in other words, not reactive toward anything, you head up towards this end. Down towards this end, it's easy on, easy off. Okay, so that's one way we think about the structure, just the bond itself and what's on either end of it. But there's also more to it than that. You can't just stop by looking at the bond itself. That's the same in all four of these structures, CX, 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 and CX. Now you have to start looking at more like the whole molecule, and there's a term that goes along with each one of these environments. So if the carbon is surrounded by nothing but hydrogens, there really isn't much you can call that other than methyl. And that all by itself is a respectable compound. Actually, they're pretty toxic compounds. Kind of bad for the environment, but okay, methyl, iodide, bromide, what have you. This one, where you have only one carbon, that starts a trend to 2 and 3. I guess you could say for methyl, there are none. How many neighboring carbons do you have? Okay, this environment is called primary, on up to secondary, and finishing with tertiary. That's what you talk about if you're describing the carbon itself. And this isn't just words, this is willingness to react. So you'll serve yourself well by learning to recognize not just words and counting carbons, but overall, on this end, you have something that on the right carbon is less crowded. On the other end, very crowded. Okay, and again, there's a trend in that direction. How crowded something is, big difference in reactivity, as in really reactive ranging to not reactive at all. Okay, we'll get to that kind of example. So let's just do a few of these and maybe stop with the labeling of them. Okay, you're going to go for the carbon that has the halogen on it, chlorine in this case, and maybe I'll mark these out to begin with. So you're looking at only one carbon in each one of these examples, and your job is to say methyl primary, secondary, or tertiary. This one right here, okay, how about if you tell me, first one, what would you call it of those choices? It's not methyl, okay. It's primary, yep. And here's where you don't want to get tripped up. There are other carbons in this molecule that have a lot more partners than this one does. That's okay, just ignore them. Look only at the carbon where the halogen sits. So if you went to this one right here, the second one, you count its number of carbon partners, one there, and what do you call that? Yep. Now again, don't get tripped up on that carbon right there. It's a tertiary carbon, right? It has 1, 2, 3 carbons as partners, but it's not the one where the halogen sits. So you can ignore it. This one right here, what would you call it? Yep. Now it's primary, although the rest of the molecule is way different from the first example, which is okay. And finally, this last one, what would you call it? Tertiary. Yeah, that one's tertiary. And just to put on a difference that's easy to put on, this one is, I should spell it right, uncrowded. This one right here, very crowded. And that's at the carbon where the halogen is sitting. Okay, now after having introduced a few differences among these characters, we're just about to look at how they react. But just a little bit first about their physical properties. Same as for alkanes. Not a nickel for the difference. Now they're a little bit heavier at a given number of atoms, right? Because chlorine is heavier than hydrogen. But at the same molecular weight, doesn't matter at all. The trends are things like, what do we say, branching lowers boiling point and melting point. So if you remember that, you don't need to write it down. Another thing is that an increase in molecular weight is going to lower boiling point and melting point. There's just minor amounts of dipole bonding possible, but really most of it is that little term we use, van der Waals. Okay, and that makes them look like what they are, pretty similar to alkanes physically. Now we will get to some other functional groups, especially if they have OHs in them. They introduce their own set of rules. But for now, not a nickel for the difference. All right, so let's move to the interesting part with the little roadmap. I'm not going to write anything on this page on purpose, because I know you won't learn anything just by looking at this, but what you can do is start to set up kind of a map. What you'll find is that there are two things that can happen to these compounds that we abbreviate Rx. They can either undergo substitution or elimination, which are exactly what they sound like. Substitution, see, if you substitute the center on a basketball team, when you're done with that little move, the team still has 5 players, right? You just pull one player out and put in another one. Elimination is more drastic sounding, and it is more elimination. If you did an elimination on a basketball team, the same way it happens in these compounds, you'd end up with 3 players at the end of the game. Okay? You're actually taking things away and not putting anything in their place. Those are the 2 possibilities. Now, within those, there are 2 options for making the same thing happen. Substitution is abbreviated substitution nucleophilic. We'll get to that term. Either 2 or 1, bimolecular or unimolecular. Same story, E2 or E1. Those 4 letters right there are like the organic 1, slough of despond, the swamp of despair, and so forth, right? Some of you have probably had some organic, you've had a brush with it in the past. Do those look familiar to anybody? Okay, you can, believe it or not, even though there are only 2 reactions and 2 options for each one of them, there are several opportunities for getting confused, so I'll try to point out what they are as we go along. That's where we're going. 2 reactions and 2 options for each. All right, so let's start this. Here are the 2 reaction possibilities. One of them substitution, and then at the bottom of the page, elimination, so we will pick that up. Okay, reaction possibilities, as always, are dominated by these 2. All right, number 1. This is starting to look more chemical, more like a reaction. And what I want you to notice is what they all have in common. Now there are several different options for these reactions right here, but look what's not changing. Here's Rx. So that's the same in each one of them. That's what the whole chapter is about. Now here in this other spot, the second reaction, is something that we call the nucleophile, meaning it loves positive charge. It can be neutral. It can have an anion. Maybe it has an extra H. Those are the stories right there. Okay, I'm going to try to keep these really small. That one's neutral. Keep these small enough they can be optional for you. This one's an anion. This one has an extra hydrogen that it needs to ditch by the time it gets down to the end. But whatever you may be looking at, they're all reacting with their other partner, and let's tell that story with a different color down here. On this side you have something that's going to behave like a Lewis acid. And that's because there's that partially positive spot on the carbon. The other reactant is a Lewis base. Okay, now I won't mark up any more, but look why, yeah, I can add just a little arrow. Look why they're considered a Lewis base. There's a prominent spot in each one of them where there's a lone pair of electrons that's aggressive enough to go after the positive spot in the other reactant. And there's one on each. Okay, get to the other side and look what has happened. Each one of these would be termed a substitution product. And then over here, this glorious term, a leaving group. Now look what you got. For the most part, in 2 of those examples, you just knock the halogen out as an anion. And it has now fulfilled its purpose in life. It was put there to go away, and when you're all done, it's done gone. It may end up with the extra hydrogen as its partner, But what you will have for sure is now in place a new bond. That's the new bond to carbon, where the old bond used to be to a halogen. Okay, that's maybe kind of what you'd expect, right? Substitution, you take one thing away, put something else in its place. Now there's a ton of different ways this can happen, and that's part of the struggle in this chapter, recognizing that there's really only two things that can happen, but there are several different versions of each one of them. That's substitution, and the other one I'm going to nominate as probably the hardest, maybe not the hardest, it's the most frequently missed kind of question in the class. So let's say that we're now in territory that's easy to miss. And here's the story. The halogen leaves. Now that much is like substitution. You won't find it in the product. But since nothing else takes its place, that means that in order to stay neutral, the molecule has to sacrifice something else. So this leaves. That's one thing that leaves. The neighboring hydrogen also leaves. So you got to have two carbons to tango in this process, and each one of the two neighbors will lose something. Okay, so here's the two carbons we're tracking in this example. And notice what happens over here. That hydrogen goes away with the nucleophile, which is a strong base. And this is a way of the nucleophile kind of making it clear. Carbon, I don't necessarily care too much about you. If the hydrogen is easier to get, I'll just take it instead. I don't care too much about you. Meanwhile, the halogen gets knocked out, and so let me add a little story about it. This leaves as an anion. And notice the big story over here. You now have an alkene product where there was no alkene before. It got created because one partner on either side of the two carbons got removed in the reaction itself. The great urge here is to, let's see how much of this I can get on screen, at least this last part here. The great urge is to say, I know what substitutions look like. They're pretty predictable. So I see a halogen here and I see a partner for it. What I need to do is go, okay, take away that halogen and put the nucleophile in its place. That's the real challenge. Understanding structures and reactivities so that you know when this is favored and this is not. Okay, there's a little roadmap now with more details on it. But so far, any questions? Okay, well, let's put some real structures on there. Enough of these general schemes and so forth. Okay, now this is going to look to you like 50 different reactions. It's actually one. This is all just one. Okay. All just substitutions. So let's go through and identify the characters. So there's Rx in that one. And it doesn't have to be written first or second. Either one will work. There's Rx in that one. And in the next two, iodine and bromine show up as the examples. And we've got a couple more. So here's Rx, and there's Rx. Okay, now that much is probably the least complicated to map out. It's recognizing the nucleophile in the other piece. Okay, now in this first one, here's your nucleophile. Now remember, it needs to have a lone pair of electrons somewhere. And if you've said it's got a negative charge on it, which this does. It's the partner of sodium plus. There's for sure a negative charge on that. That's the nucleophile. Now, here's same story. OH minus, sodium hydroxide, remember from freshman chemistry, cation, anion. There's your nucleophile in that one. Okay, the next one is still the same reaction, except here, remember that the nucleophile is neutral. This pen is dying, isn't it? Okay, now there'd be a couple of lone pairs on that oxygen, just to remind you. And then you move on to the next one, and it looks like we are back. We're back to a nucleophile that's an anion. Okay, there's a full Lewis structure there. And then you come to this next one. Now this is deliberately on the weird side. Okay, we're a long ways from sodium hydroxide here, but don't worry. Anything that's the anion, that's your nucleophile. So it's everything except the potassium, which is a cation, and you end up with a new bond between the nucleophile and the spot where the halogen used to be. We'll come to that on the product side. Let's finish our characters. Okay, down here is your nucleophile. That's neutral. Oh, it looks like on the first pass I forgot this bottom one. So here's Rx. And right here is your nucleophile, which is neutral, no charge. No extra hydrogen. That's okay. Let me mention a spot or two where there was an extra hydrogen. Up here, there will be one. You can tell that by looking at the product. And here's another one. On this one, we've got an extra hydrogen that can go away in the final product. Okay, now I wish I could get all these on all at once, but given what you can see, how about telling me which one of those looks like, I wouldn't have caught that one. Any of them so far? Okay, so I'm going to star now the spot that came in from the nucleophile. Here's your product. And then this piece right here is from the nucleophile. And notice, because of the way this is drawn, it's easy to tag the new bond. And you have the halogen that left as its leaving group. What do we got here? There's the new bond right there. The nucleophile came in and said, I am substituting for you iodide, get out. Which it did. Okay, next one makes iodine the aggressor. And here's the new bond. And that. Now by the time you get down to this next one with the ring and the sulfur and everything, it's starting to look kind of elaborate. That's true. I don't know, maybe it might help to tag a carbon here. That one right there is going to be the spot where you have a connection between the nucleophile and the old carbon. And to draw that cleanly, you need to draw one of them backwards, right, just to make it easy. So the carbon that you're following would be that one right there. And the new bond is this one. Now, this is the same process as in all the others. The characters look like they're more complicated. You may have to draw something left to right or right to left, but it's the same process. And that even goes for this next one down here. Okay, right here, is the bond to bromine that breaks, so that by the time you get here, there's the new one. And all of this stuff, that's the nucleophile. Let's see, I guess I didn't label this one up here. Yeah, let me go ahead and label this piece. That much is the nucleophile because it is what knocked out the halogen, iodine in that case. So this aggressive newcomer ends up with its piece, its share, and its new connection to the molecule. Here is where the Rx is actually the smallest piece of the whole thing. But go ahead and do exactly what you would have done with any of the others. You say, okay, we're going to have a bond, a new bond, from the nucleophile to the R group. So there it is. And that means that the whole thing, when you're all done, has to be positively charged. It's a cation because nitrogen now has 4 partners. Gives it a formal charge of +1. The halogen got knocked out. So you now created an anion cation pair. But it's the same process. If you track all of the characters, the charges just are what they are. And we'll come up with some more examples of these. But I want to go back through these and see what questions you might want to ask on them. This is one reaction. That's the challenge, right? Seeing all these things as being the same thing. By the way, by the time you get down to right here, that's starting to look like some of the early antibiotics. People knew how to do exactly this kind of reaction. That's why they could make the reaction, make the antibiotics they did. Questions on any of that? Okay, so this is concentrating more now on substitution. Now remember, we said there could be 2 different ways to make substitution happen. The outcome is the same either way, right? You end up with one thing going away, another thing taking its place. So here's option 1, which is SN2. And this right here, you're drawing a mechanism, needs to look like this. Okay, the mechanism is details. If you already knew that, you're good? Okay, so there will be a curved arrow, and you start from the nucleophile, and you realize, let me add this one more time maybe, that partially positive charge is there on that carbon, which makes it this irresistible spot to a nucleophile, which comes and it creates something that I can now tie back to the diagrams we drew for potential energy. Now notice right here in the middle, you've got something that doesn't look right for the carbon involved. Look, that's 3 real bonds and 2 pretend bonds to carbon. That's 5, that's too many, meaning that neither one of these dashed ones is real. One of them is breaking and the other one is forming. So that's why we say when it reaches that point right there, where you're partly formed with the new bond and partly broken with the old one, that's the transition state. That's as difficult as it gets when both partners are still interacting a little bit. This thing is so unstable that there's no way that you will ever isolate it. And by the way, transition state is not the same thing as an intermediate. Keep that distinction in mind. It's unstable, it can't be isolated. This is now at what we would have said was the top of the curve in the potential energy diagram. It's also, this transition state is in the middle of one step. It is not a separate step to itself. Most mechanisms that you draw will not require you to draw a transition state. This one is, I don't know, maybe we're starting with the exception. This one is so important because it explains what happens. Look at what you have when you're all done. Here's the product, and the other product is the leaving group. And what you want to be able to follow is the stereochemistry. So that's the final point that I'm going to make about the transition state. So this explains the stereochemistry of both the reactant and the product. I think the product is all I need to write to mention that. Okay, so here are some facts that you can kind of put together on a quick little diagram. So let's just do that. Potential energy, reaction progress. This is one step, and it is spontaneous. That's pretty well known. Here's the transition state up here. Now, the reason we call this SN2 is that there really are two things that have to smack into each other in the slowest step. Okay, two things in the slowest step. It so happens that the slowest step is the only step. That's the only one there is. That won't be the case when we get down the road a little bit. As far as an intermediate goes, you got none. The stereochemistry is inversion. Okay, and that's because the nucleophile pushes out I minus from the opposite side. All right, there's a little fact and a little concept built into each one of those spots. Bimolecular, that's why we call it SN2. Stereochemistry inverts, and the way we draw that is like this. Everything swaps sides, P2 and P3 swap sides, but they stay pointing out or back. Since the other one, though, the newcomer is in the position directly opposite that leaving group, this is like going R to S or S to R. I'm being careful what I say, because if your nucleophile has a different priority, it can mess up that little rule. This is like going from here to here. That's inversion. It's literally like taking an umbrella and blowing it inside out in the wind. That's the stereochemical piece of it. That's SN2, and we will call that option 1, which is done as of this point. One step. Okay, so there's confusion point number 1 to be thinking about. SN2 doesn't mean 2 steps. It means 1 step. I'll come back to that again. Okay, we're out of time. Better call it done right there. I'll see you Wednesday with quiz. Do.